Hi, this is Rishik, and I'm going to take you into a walkthrough of my internship project, which I'm currently working on at National Instruments, Bangalore. The project basically consists of an RCP or rapid control prototyping of an IC spark ignition engine, which consists of a single cylinder engine. So here we have on the right the cylinder piston arrangement with the intake manifold, the exhaust manifold, the inlet valve and the exhaust valve, the spark ignition system, the fuel injection system. So basically we are going to see a simulation of the cylinder piston movement based on the parameters provided. So on the top left corner we have the controls. By varying the loop delay we are going to change the RPM. If we increase the loop delay we are going to decrease the RPM, and vice versa. The test button over here is mainly just to turn off the simulation when it is not on. The stop button is used to stop the simulation as required. Then based on the given inputs we are expecting some responses. So since the simulation is RPM driven, we are basically expecting a pedal position sensor output. So we have a maximum of 45 degrees in the pedal position. This corresponds to the accelerator in a motorbike or a car. We have a throttle position sensor over here which varies from 0 to 100 degrees. We are also determining Boolean values for under travel, idle throttle, the wide open throttle, the over travel. The under travel is basically the indicator which gives us the indication that the air supply is just too meager, and hence the throttle is just choked, and hence the engine may shut down. The idle throttle corresponds to the throttle position that is required to maintain the engine in an on state. The wide open throttle indicates that the throttle is configured for a maximum torque. Over travel indicates that there is just too much of air supply, and hence the engine may shut down. The throttle angle indicator over here indicates the angle that we are generating depending upon the RPM. We have a throttle sensor voltage. We actually collected a lookup table from a manufacturer, depending upon which we are able to estimate the voltage that we are expecting depending upon the throttle angles. Suppose we change the RPM, we are also changing the throttle position over here, and we are also expecting a change in the throttle sensor voltage. So the maximum voltage that we are able to generate is 5 volts and the minimum voltage is 0 volts, but we are not getting a 0 volt right now because it is in idle condition right now. Next we move on to the engine specifications. The first is the connecting rod length, the crank rod length, the idle throttle position, the closed throttle position, the diameter of the piston, and the displacement volume. We can change the parameters as required, but then we'll also have to change the size of the cylinder in order to fit in the given specifications. Then we have the environment specification. We have an input for the coolant temperature. Based on the engine coolant temperature we can have 4 phases of working of the engine: the startup phase, the warm-up phase, the normal running condition, and the overheated phase. These inputs can be taken into the ECU and then configured as required. For the atmosphere pressure we have 1 bar, for the adiabatic constant we have 1.4, and the manifold pressure is assumed to be a constant, that is 0.54 bar. The ambient temperature is assumed to be 305 Kelvin. Next we move on to the engine dynamics, the parameters that we are expecting to change once we change the input, that is the RPM. Once we change the RPM, there is going to be a change in the throttle angle sensor, based on which we are going to have a change in the throttle area that is available for the air to get in to the intake manifold. This is the RPS indicator over here. Then we have the airflow indicator. Basically when we are increasing the throttle angle, what we are doing is we are allowing more air to pass through, and hence the amount of air going into the intake manifold increases. So as I increase the RPM, there is an increase in airflow. Right. The volumetric efficiency is a function of the manifold pressure, which is assumed to be a constant over here. The manifold flow to cylinder, that is also dependent upon the manifold airflow, but because we are modeling the entire system based on an orifice flow model, so the mass of air going into the cylinder is different from the mass of air coming into the intake manifold. Then we move on to the electronic control unit. The ECU code is basically meant for a single cylinder engine right now. This is the crank angle indicator, which is incremented 10 degree each iteration. Then we have the fuel injector. The fuel injector value, or the pulse width that we are obtaining over here, basically depends upon 2 parameters, that is RPM and the coolant temperature. Now this value over here, the fuel injector RPM, is the pulse width that is generated only depends upon RPM, and this is a scaling factor that has to be multiplied with this factor to get a pulse width that is used to optimize the engine performance. Then we have the spark advance, that is the time before the TDC, before which we are igniting the fuel. So based upon the RPM, we are generating a spark advance value. As you can see, if I am increasing the RPM, the spark advance decreases, and when I decrease the RPM, the spark advance increases. Right. Also we can see over here, based on the simulation, we are timing the spark advance and the fuel injection process as given in the simulation. The exhaust valve and the inlet valve are also timed according to the simulation, so we are able to generate a 4-stroke engine simulation with the varying parameters over here. Then we have the crank sensor. This basically is a rotor having teeth. It has a few teeth missing from it just to identify the TDC events. So it is now configured for a 12 teeth with 2 teeth missing, that is, it has a net 10 teeth right now, and hence we are expecting 10 sine wave pulses as expected. We can change it to suppose 6 and 1. So now we are going to expect 5 pulses with 1 missing. Right. So the main advantage of the RCP over here is we are generating the mathematical model of an engine and testing it with a software ECU. This can be later implemented for a hardware in loop simulation, in which we can test the industry standard ECU with a mathematically modeled engine. Also over here we can see, because we can see the simulation in real time, it becomes easier for the viewer to actually visualize the whole process. Now because the process was implemented using the Windows operating system, the RPM values that were generated were unrealistic, and hence a scaling factor has been used to get realistic values for the RPM. So as you can see, we have a idle value of RPM of 1700 RPM approximately, and a maximum RPM of 9000. Right. Also in the simulation we can also change the inlet valve and the exhaust valve timings and then see for optimal performance. Right now the manifold pressure is assumed to be a constant, but if it is made a function of the manifold airflow, then we can also generate the torque characteristics and hence estimate the torque depending upon the given RPM and the airflow value. And also the ECU module over here can be upgraded as required. Basically an algorithm based on the lookup tables available for spark advance and ignition timings were used to obtain the values for spark advance as well as for fuel injection. So depending upon these values we are able to control the engine parameters. So that basically does it for the project, and thanks for your patience.